Hey guys, we are going to talk today about some applications of differentiation. And we're going to talk about applications of differentiation for several lessons. So the first application we're going to talk about is linear approximation. And so the idea behind this is that we can use the derivative at a point because all that is the slope of a tangent line. And close to that point, we can use this linear equation to approximate values of our function because the linear equation will also be close to the function. And the formula, how we actually calculate it, just comes from the definition of the derivative. So if we know that as delta x gets really small, the change in our function over the change in x is just the instantaneous rate of change at x, which is just our derivative. So what we can do is we can use this equation to approximate a interval of our function f close to x. And all we have to do is take the derivative at some point x and multiply it by the change in x. Generally, we would write it like this. We would be given some point a, and so it would be f prime of a times delta x. We'd also be given delta x. Another way that we can do this is we can also write a linear equation that will approximate f of x where it's close to some a. And so our linear equation would look like this. We're still just using that definition of the derivative, and it would just be the derivative evaluated at a, which is like our slope, times x minus a plus f of a. So really, this is a lot like the point slope form of your of your line. We're just solving it for f of x. And this will approximate values of x that are close to a. So let's try an example. So let's try to if we're given some function f of x is 1 over 1 plus x squared, and then we want to approximate this at a is equal to 3, and we want to find the interval of f where delta x is equal to 0.5. So the first thing I would do, since if I go up and I want to approximate delta f, this is what I want. So I want delta f when a is 3 and delta x is 0.5. So I go up to my formula for delta f. So it's just going to be f prime, oh, I'm so sorry, f prime of a times delta x. So I'm going to need to find the derivative of f, and then I'm going to need to find it evaluated when a is 3. So my delta f is approximately, it's important that you use squiggly equal lines because we're just doing an approximation, is going to be approximately f prime of 3 times delta x. So my f prime of x is going to be, I am going to rewrite this as 1 plus x squared to the negative 1. So then I'll end up with negative 2x, because I'll do the chain rule, all over 1 plus x squared all squared. And so now I want to find f prime of 3. F prime of 3, when you plug everything in, is going to be negative 0.06. I also will need, well, I'll need that in just a minute, so I'll deal with that later. So let's go ahead and write our equation. So delta f is approximately f prime of 3, which is negative 0.06, times delta x, which is 0.5. So we get that delta f is going to be approximately negative 0.03. So here's our approximation. So let's go ahead and check and see how accurate we are. So we actually have a formula for error. And so it's pretty obvious what the formula would be. It's your actual delta F minus your predicted delta F. I guess thinking in terms of statistics today. So let's say it's the actual minus the approximated, the one that you've calculated. So I mean, I have a calculator. I can calculate what delta F is going to be on that interval. And so that's just going to be F of 3.5 minus F of 3. Because all I'm doing, my delta F is just the change in F when between x equal 3 and x equal 3.5. So I can find f of 3.5. It's just going to be 1 over 1 plus 3.5 all squared. Minus, since I'm looking at over this interval, f of 3, which is 1 over 1 plus 3 squared. So this would be my actual. And then if I want the error, I'm going to subtract my approximation, which is negative 0.03. All right, so when I do the math here, I get negative 0.0506 as my actual. So my error is going to be negative 0.0206, which seems like a fairly small error. But when you're looking at a value as tiny as negative 0.0506, it's actually a fairly large error. One of the reasons that we get such a large error here, because in other problems you'll actually get a fairly small error, is because of the size of delta x compared to our values. So our delta x is 0.5. Our actual value is fairly small. So because delta x is so big, we're going to get a fairly large error. Let's calculate the percent error. So your percent error is just going to be your approximated value divided by your actual value. And we're going to take the absolute value of this because we don't want the percent to be negative. And of course, that'll be a decimal. So to make it a percent, we'll multiply it by 100. So my approximated value, having a hard time today. Your percent error is your error divided by your actual times 100. So my error was negative 0.0206 divided by my actual, which is negative 0.0506 times 100, obviously. So this gives me an approximate error of 40.7%. So that's a pretty large error. You should get closer to 5 or 10% if your delta x is smaller. So the other way that we can approximate is we can actually create a linear function like this that will approximate values close to a. So let's see if we can do an example where we write one of these. So if my y is equal to 1 plus x to the negative 1/2, I want to create a linear function that will approximate f close to x equals 0. So let's think about this equation. The equation that I need to use is going to be sorry about that. F of x is equal to f prime of a times x minus a plus f of a. So I'm going to need to find the derivative of my function evaluated at 0, and then I'm also going to need to evaluate my function at 0. So I'm going to start by evaluating my function at 0. And so that's just going to be 1 to the negative 1/2, which is just 1. So now let's go ahead and find our derivative. So y prime is going to be, let's see, negative 1/2, 1 plus x to the negative 3/2. I'm not going to worry about cleaning this up because the only thing I need it for is to find y prime of 0, which is going to be negative 1/2 times 1 to the negative 3/2, which is just 1. So y prime of 0 is going to be negative 1/2. So now what I can do is I can write my equation. I have all the pieces. I know a, I know f of a, I know f prime of a. So my f of x will be approximately f prime of a, which is negative 1/2, times x minus 0 plus f of a, which was just 1. So I could clean this up a little bit more, and it's just going to be negative 1/2 x plus 1. And so close to 0, this will be an approximation for my function. It's pretty neat. So another really important application in calculus in terms of derivatives is extreme values. And we really have three kinds of extreme values, and so it's important to understand the difference between the three. The three kinds we have absolute, maximum and minimums. We have local maxes and mins. And then we also have critical points. So generally when you look for maximums and minimums, you look on an interval. So let's talk about an interval and what happens here. So an absolute maximum or minimum is just the actual highest or lowest point on the interval. So this could be hills, I would call them hills, it could be valleys, or it could be endpoints. Local maximums and minimums are just the maximum or minimum value over an open interval close to that value. So these are only going to be, because we don't consider endpoints when we're on an open interval, these are just going to be hills and valleys. So critical points are kind of they kind of encompass everything. So critical points are going to be, the definition is it's going to be where f prime of c is equal to 0 or f prime of c does not exist. So these can be cusps, they can be points, they can be all sorts of things. So we can find another neat thing about hills and valleys is that their derivatives are always going to be equal to 0 because at hills and valleys you're always going to have a horizontal tangent line. So one of the ways to check for maxes and mins over an interval is to take the derivative, set it equal to 0, and then find those places where you have horizontal tangents. Then also check the endpoints, check all the function values, figure out which is the biggest and which is the smallest. Critical values aren't necessarily hills and valleys. you could have something like this where at 0 we have a horizontal tangent, but it's not a max or min. So let's take a look at critical values first. So let's look at an example. So we're interested in finding all critical points for this function. So f of x is equal to x divided by x squared plus 1. So we want to know the places where if we want all critical points, then we want the places where f prime of x is equal to 0 or f prime of x does not exist. So immediately we need to take our derivative. So we have that f prime of x is going to be, we had used the quotient rule, so it's going to be the derivative of the top, which is 1, times the bottom, minus the derivative of the bottom times the top, all divided by the bottom squared. So let's clean it up a little bit. So we'll end up with negative x squared plus 1 all over x squared plus 1 all squared. So we're interested in places where this doesn't exist and where it's equal to 0. So it actually is kind of fun the way it ends up. It's not going to exist where the denominator is 0, because that's the only point in our domain that we have issues. It's also, and it's going to be equal to 0 where the numerator is equal to 0. So we have kind of two things. F prime of x equal to 0 is just going to be where negative x squared plus 1 is equal to 0. So this is going to give me x squared is equal to 1. So x would be plus minus 1. So we're going to have critical values at positive 1 and negative 1. That's where the derivative is 0. Now we want to know where f prime of x does not exist. And this is going to be where x squared plus 1 all squared is equal to 0. And if you do the math, you actually end up with x squared is equal to negative 1. So you will know there are no points where f prime of x doesn't exist. You always need to check, though, if you will have issues in the domain of f prime. So now we just want to write our statement. So the critical values for f of x are at x equal positive 1 and x equal negative 1. So now let's talk about maximums and minimums. So let's try to find all the maximum and minimum values on a closed interval. So let's take a look at this equation. So we have y is equal to x cubed minus 6x squared plus 8. And we're interested in the interval from 1 to 6. So what I need to do is I'm interested in finding the f evaluated at the endpoints, and then I'm also interested in where f prime is 0. And then the smallest of these is going to be your min, and the largest of these is going to be your max. So make sure to check your endpoints. That's the biggest issue I see with students here. So we're going to start by finding y prime. And it'll be 3x squared minus 12x. And then we want to know where this is equal to 0. Sorry about that. We want f evaluated at the endpoints to see if those are maximums and minimums, and we want where the derivative is 0. Sorry, not evaluated at 0. So if we want to set this thing equal to 0 and solve, then I'm going to factor out a 3x, and so I'm going to get that 3x is equal to 0. which implies that x is 0. And I'm also going to get that x minus 4 is equal to 0, which gives me that x is equal to 4. So these are my two critical values. So now I want to test and see which has the smallest function value and which has the largest function value. These will be my maximums and minimums. So I have to test all of these things. I have to find f prime of 0. I have to find, I have to find f of 0. I have to find f of 4. I also have to check my endpoints, and they're 1 and 6. So I have to find f of 1, and I have to find f of 6. And if you're able to use a calculator on this problem, I would suggest plugging the equation into y1, the original function that's given to you, and then just using the table function and then finding the values. You'll make less mistakes that way. All right, f of 0 is equal to 8. If you plug in and do the math, f of 4 is equal to negative 24. F of 1 is equal to 3. And then f of 6, oh, that's equal to 8 also. So it looks like over this interval, I actually have two maximum values, which happens because they're both 8, and then I just have one minimum. So now I can make my statement and draw my conclusion. So the maximum over 1 to 6 is R. I guess I should make that plural then. R08 and 68. And the minimum value is for negative 24. So this is an excellent application of differentiation, and you can apply it to a lot of things. When you optimize, it's you're always interested in finding the maximum and minimum values, so you can apply it there. All right, I hope you guys have a good day. Thanks so much.